In this experiment, proton nuclear magnetic resonance spectroscopy, (NMR), is used to identify the unknown organic compounds. Nuclear magnetic resonance, NMR, is a spectroscopic technique that detects the energy absorbed by changes in the nuclear spin state. An NMR instrument allows the molecular structure of a material to be analyzed by observing and measuring the interaction of nuclear spins when placed in a powerful magnetic field. The NMR machine comprises of a magnet, produces strong magnetic field, a radio frequency source, a detector, and a recorder. Here is an example of an NMR spectrum of ethyl bromide. NMR spectrum is a plot of frequency applied against absorption. A signal in NMR spectrum is referred to as a resonance. The x-axis is the chemical shift, which indicate at what frequency the hydrogens resonance. The chemical shift of each proton is compared to the standard reference, tetramethylsilane, TMS. TMS has chemical shift at 0 ppm. Depending on the environment surrounding the protons, the chemical shift of protons in a molecule can vary. A proton that has a higher ppm value is called downfield, or deshield. When it has lower ppm value, it is called upfield, or shielded. The chemical shift of various protons in a molecule can be found in your lab manual, page 90, or the back cover of your lab notebook. Let's review this NMR spectrum. In this example, the green hydrogens in the ethyl bromide is closer to the bromine. The green hydrogens has a higher ppm, downfield, because of the deshielding effect from the bromine next to it. The deshielding effect on the blue hydrogens is less compared to the green hydrogens. Therefore, the signal from the green hydrogens is at 3.5 ppm, while the blue hydrogen is at 1.75 ppm. From the NMR spectrum, the relative number of protons can also be determined. The area under the NMR resonance is proportional to the number of hydrogens which that resonance represents. The ratio of the integration values is equal to the ratio of each types of protons in the molecule. For example, in the ethyl bromide NMR spectrum, the integration ratio of each type of proton in the molecule is 2 to 3. From the NMR spectrum, the information of the neighboring hydrogens can also be identified. NMR provides information on how many hydrogen neighbors exist for a particular hydrogen or group of equivalent hydrogens. In general, an NMR resonance will be split into n+1 peaks, where n is equal to the number of hydrogens on the adjacent atom. Let's look at the ethyl bromide example again. Let's analyze the blue hydrogens. The blue hydrogens has equivalent of 3 hydrogens. Adjacent to the blue hydrogens, there are equivalent of 2 green hydrogens. Therefore, n is equal to 2, so n+1 is equal to 3. Why? The signal from the blue hydrogens is splitting into 3-way, or we call it a triplet. Similarly, the splitting of the signal from the green hydrogens can be determined by looking at the number of equivalent of blue hydrogens. The signal of the green hydrogens is split into 4 ways, or a quartet. Here is another example, the NMR spectrum of ethyl acetate. From the proton NMR analysis of an organic compound, a few information can be obtained about the molecule. The number types of hydrogen, and also the environment surrounding the hydrogens. The relative number of the hydrogen, and the number of neighboring hydrogen. This is how to analyze a sample, using the NMR in our laboratory.
Turn off the standby mode if the instrument is on standby. Remove the sample and replace with the sample to be analyzed. The sample tube is a long and skinny tube, so be careful when inserted into the sample holder. When the sample is ready, hit Go button on the screen. And wait until it is done scanning. First, zoom the area of interest. Then, process the signal to fix the phase and baseline. Next, set the chemical shift of the TMS reference to 0 ppm. The TMS peak is usually the one all the way to the right, and close to 0. After that, integrate the peak area of each type of hydrogen. Then, adjust the area to be integrated, if necessary. Finally, set one area as the reference for the number of hydrogen. This will adjust the ratio of the relative number of hydrogen. When that is done, you can print out the spectrum. Carefully pull the sample tube out from the sample holder